Matter is made of atoms. This was a speculation, as we've heard, by Democritus 2,500 years ago. But he didn't have any data or observation or experiment to support the hypothesis. In the early 20th century, elegant experiments by Rutherford and others showed that there were tiny indivisible particles that we call atoms. The structure of atoms was only unveiled by high-energy physics experiments through the middle part of the 20th century. And in fact, if you ask the question, when was the first individual atom imaged, that only happened within the last 20 years. But the evidence for atoms is compelling. Atoms are real, and they compose everything in the universe. In this series of zoomed images, we go in orders of magnitude, starting with a familiar situation, grains of sand. An individual grain of sand may be a millimeter, down to a few tenths of a millimeter. At 10 times zoom, we can see the individual grains of sand. If we increase the zoom to a factor of a few hundred, now the individual grains of sand start to take up the entire view, and we're looking at the details of the mineral that compose sand. We're still not able to see individual molecules, but large numbers of molecules. Going in another order of magnitude to a factor of 10 or 100,000, the individual crystals now devolve into planes that correspond to the molecular layers within the sand, which is silicon dioxide. Another order of magnitude or so, and those individual molecular layers are now visible. And going into the final level of zoom, which is 100 million times, individual molecules are now visible, composed each one of 3 atoms. This is the method that's only been developed and perfected in the last few decades that allows us to inspect matter at the atomic level. What is the basic structure of matter, or structure of an atom? In the 19th century, it was thought that atoms might be billiard balls or BBs, tiny, indivisible particles, hard-edged. But experiments by Rutherford and others in the 20th century show that that is not the case. Rutherford's elegant experiment shows that atoms are mostly empty space. When he fired charged particles through a thin gold foil, much to his surprise, most of those charged particles passed straight through, as if the atoms weren't there. And we know from his experiments that atoms are 99.999999999% empty space. Occasionally, a charged particle would violently recoil from the nucleus of an atom. And from that violent recoil, in the same beautiful set of experiments, Rutherford concluded that the atomic nucleus is small, dense, and charged from the protons within it. The combined picture we get from these experiments is of a tiny atomic nucleus housing 99.9% of the mass of every atom and a diffuse cloud of negatively charged electrons occupying most of the volume. Atoms are incredibly small. If you put them edge to edge, a trillion would fit across the head of a pin. A scale model that gives us a sense of the scale within the atom would be a football stadium, where a baseball sits at the 50-yard line. That's the atomic nucleus. And the electrons orbit in a cloud at the outer edge of the stadium, in the upper parts of the stands. That shows how much is empty space in the atom, where a tiny percentage of the mass occupies the large volume. Most of the mass is in that baseball at the 50-yard line. And then the next atom would be a football stadium away. This is the emptiness of normal matter. The fact that matter feels solid when you run into a wall or step your foot on the ground is an illusion due to the electrical force that keeps atoms apart in normal matter. Other terminology that we need in terms of atoms is the distinction between atomic number and atomic mass. Each unique atomic number corresponds to an element, and that is the number of protons in the nucleus. 1 for hydrogen, 2 for helium, 6 for carbon, and so on. Atomic mass, however, involves the entire mass of the nucleus, which is a combination of neutrons and protons. Neutrons and protons have about the same mass, but neutrons have no electrical charge. The uniqueness of an element comes from an equal number of protons in the nucleus and electrons surrounding it. Neutrons do not play into the electrical force because they have no electric charge. We define an isotope of an element as a version of that element with a different number of neutrons. Remember, the varying number of neutrons does not affect the chemical behavior, and so it is the same element, but it's an isotope because it has a different mass. Some isotopes with large numbers of neutrons relative to protons can be radioactive and decay. Molecules are one or more atoms held together by the electrical force. There are many types of molecules. In the universe, over 120 different molecules have been detected, mostly in cool interstellar space. On Earth, because of our technology, tens of thousands, perhaps millions of different molecules have been created in the lab. A compound is a mixture of molecules not naturally forming, basically a mixture where they are not held together by their electrical forces. Organic compounds, or organic materials, are those that specifically involve the element carbon. We've seen that the solidity of matter is essentially an illusion of the electrical force. These experiments, of course, were done over 100 years ago. More recently, with high-energy physics experiments in accelerators, we can pick apart atoms and show in detail how they're made. The nucleus of an atom in particular is an impregnable fortress held together by the electrical force, one of the strongest forces of nature, far stronger than gravity. So it takes extraordinary energies to break apart an atomic nucleus. Much smaller amounts of energy required to take electrons from an atom and ionize it. Since we're dealing with extremely large numbers in this class, we'll use orders of magnitude to characterize the number of atoms in different familiar situations. Let's start with our grain of sand. The grain of sand, made of silicon dioxide, contains roughly 10 to the 19 atoms. That's 10 billion billion. A human contains roughly 1 billion times more, the equivalent of 1 billion grains of sand. And most of humans are composed of water, H2O, plus some carbon, nitrogen. That total number of atoms is 10 to the power 28, a 1 with 28 zeros after it. Taking the Sun as a typical star, the number of atoms in a star is 10 to the power 57, a 1 with 57 zeros. And in the case of stars like the Sun, almost all of those atoms are the simplest two elements, hydrogen and helium. Going up to the next scale of structure in the universe, we have galaxies. A galaxy will typically contain about 100 billion stars, and that corresponds to about 10 to the 69 atoms, a phenomenal number, 1 with 69 zeros. And perhaps the largest pure number in science is the number of atoms in the universe, composed of about 100 billion galaxies in the observable universe. That number is 10 to the 80, a 1 with 80 zeros after it. Now obviously no one has ever counted that number of atoms, much less the number of stars in any one galaxy, nor the exact number of galaxies in the universe. This is how astronomers use estimation, or projection, or extrapolation, to derive overall numbers about the universe we live in. To summarize atoms, the evidence for atoms has become extraordinary in the last few decades. We've been able to inspect within normal matter and see individual atoms and make images of them. There is no doubt that atoms exist. We can understand the universe in terms of the atoms it contains, many of which are single atoms and some of which are composed into molecules. Most of the universe is made of the simplest two possible atoms, hydrogen and helium. We can characterize the typical number of atoms in terrestrial everyday objects, like human beings, or in stars, galaxies, and the universe itself, leading to one of the largest numbers in science, 10 to the power 80, the number of atoms in the visible universe.